please go to the folder Documentos again, and you can enter in the folder SWGO. Ah, okay. Let's give 2 more minutes. Oh. Oh. Okay, everyone. So, for those who just arrived, please open the directory Documentos and then SWGO. Okay. In this directory, please you can open the terminal. Right-click, open terminal. Inside the folder SWGO, which is within the folder document. You find it? Okay. Open the terminal. Mamba activate PySvigo. Okay. Mamba activate PySvigo, okay, and then Jupyter notebook, okay. You should see something like this, and then please open the notebook called 1 ICTP make data set. Did you manage to open the notebook? Yeah. Okay. Okay. Open. Okay. Okay, everybody. So the analysis of today will be a bit different. For the imaging atmospheric Cherenkov telescope from yesterday lesson, I told you that we had one run equivalent to 10 minutes of data, and then with the brute force, I generated 3 extra runs to perform the analysis. For SWGO, we don't have it. So we are a step before, okay? We are using simulated, we are simulating data, okay? Trying to simulate a detection with this new telescope. We will start by creating these empty objects like we did for the CTA, for the imaging atmospheric Cherenkov telescopes. And then let's start by loading the data. Just shift enter. This is the data in the folder IRFs inside the directory that we are working, the instrument response functions. And then please load these libraries. This is basically Gamma Pi, but also we are using a lot of AstroPy as well. Okay. Okay, are we all at the same time? I don't know, people are arriving a bit late. Okay, this step here, make Benedict, this makes reference to this script here. So we are not going into detail here, but it's just a dictionary. This was supposed to be inside Gamma Pi. However, in this version, it's not yet, or inside PySvigo, but in the future it will be inside, so we don't need to do this kind of thing. Keep in mind that PySvigo is a software under development. It's very different from Gamma Pi and Fermi. okay, which are more, we have more stable versions. So we have to do this kind of naive stuff, naive things in order to go. Okay, so before proceeding with the analysis, I think it's a good idea to give you an idea of the tanks. I hope you can see it. So there are lots of proposed tanks for SWGO. The tank that we are analyzing here in this tutorial is the tank. Okay, I choose this tank because this is the kind of tank that we have in Brazil in CBPF. Okay, in Rio de Janeiro. But every tank we give a different ladder, and every array configuration we give a different number. For instance, this is the A tank with the one array configuration. Okay, so we have a lot of tanks in the inner side. It's a very compact region. The parameter that we call view factor, which is how much of the area inside of this disk is filled with tanks, is 80%. So 80% of the area there is occupied by tanks. And on the right we have the D1, which is this tank here, which is larger than the tank A, in the one configuration. So the array configuration is the same, but the tanks are different. Okay, this is just to give you an idea. This is a very useful table for people doing SWGO, where we can see the differences between the different tanks and arrays. Okay, so we have the view factor in the zone 1, which is the internal zone, and the view factor given by FF here in the external zone. Here we define the parameters that we are going to use, it's interesting to tell you that it's useless to put a very high energy, to set a very high energy resolution in this analysis. We set it by hand. But if we set it above 70, for instance, we are going beyond the resolution of the instrument, the energy resolution of the instrument, which will be around 25 up to 15% in the best case scenario. So you can add more bins, but it will not be useful for you. Okay, to just make the analysis a bit slower. So the array we are using is the D1, because the D tank is the one that we have in Rio de Janeiro. I want to do the analysis with this tank. We're setting 17 energy bins, and this is the energy range. Okay, so this is the energy range ascension. This is the tank that we have in Rio de Janeiro. I want to show, this is the prototype. And it looks like a normal water tank, but actually it's really amazing when you climb these stairs and open this lid, because it looks like, it's like the universe disappears there, because it's so black that it's surprising. It's a brighter place. It's not. The place is not. It's very luminous. But if you open the lid, you see nothing. Okay, it's really black inside. It's a really amazing instrument. If you go to Rio de Janeiro to CBPF, tell me, it will be a pleasure to me to bring you to see this thing. Okay, just don't fall inside of it, because you may get lost. Okay, here's a tricky part. This dictionary is the dictionary that we generated with the script. So this is something that we have to use now, but we will not use in the future with PySvigo. And these are the slices, these B names, these are the slices of the sky at which we are working, okay? And we have to merge it, which will not be necessary again in the future. So we are doing a lot of almost amateur stuff here, just because PySvigo is under development, okay? So it will change a lot in the future. Okay, this is a curious step. We are setting the observation table to the drift mode, because SWO works in a very different way from MAGIC and CTA, which are pointing and following the target in the sky. SWO, no. We have the fixed tanks, and the sources are moving across the sky, and we have to take this drift of the sources into account. Okay, so we have to set this here to drift. Oh, hi. Okay. Now, oh, I'm missing just one thing that I'm sorry. Just one of the students asked me about this, and I thought I put this in the notebooks, but they didn't. Okay. One of the students, yes, maybe you, asked me about graph neural networks for the detection of the particles, right? Of gamma rays and cosmic rays. So this is the array in the configuration 1. So it may be, I don't know if it's A or D or whatever. And this is the simulation of the strike of a gamma ray shower in the instrument. So the shower hits the instrument on the border, and here we see that these yellow tanks are where the particles arrive at first, while these orange ones are where the particles arrive at later. And we can use this technique, the graph neural network, to reconstruct the particle, okay? The direction and the energy and the classification of the particle. This, on the other hand, is the charge accumulated in each one of the tanks. Okay. Do you know actually what's the advantage of building an instrument like SWGO instead of just making a larger CTA? Do you have an idea? First of all, the cost. SWGO, one tank costs around $3,000. Okay. If you go to CTA, the smaller telescopes, the SSTs, each one costs $1 million. Okay, so you can try to cover a large area with these telescopes. This would be nice, but they are very, very expensive. Okay, the tanks are $3,000, so it's very interesting cost benefit. Another limitation that we have with imaging atmospheric Cherenkovs is that once the cascades become very energetic, the showers hit the ground. For CTA, for instance, the focus of the telescope is at more or less 10 to 12 kilometers in the atmosphere. It's very different from optical astronomy, where the focus is on the infinity. So in gamma rays, we focus the telescopes at 10 to 12 kilometers in the atmosphere. Okay. However, if the showers are too big, because the original particles are too energetic, the showers will hit the ground. You cannot focus your telescope for the showers that hit the ground. Okay. So there is this physical limitation, not only the cost, but also the physical limitations that forbade us to go to the extremely high energies with imaging atmospheric Cherenkov telescopes. Okay, so SWGO, water tanks telescopes actually enters as a solution for this problem. And putting these telescopes at high altitude is another advantage, because we allow the instrument to detect lower energy gamma rays, lower energy showers, because those that would not arrive to the sea level can arrive to the top of the mountains. Okay. And for you that asked me about the paper of this graph neural network, I don't know if you already looked for the paper, but it's this one by Jonas Lombitz. I don't know how to pronounce his name. Okay. I think it would be very useful. It's a very nice book. I had the opportunity to read it when it was on archive, not published yet. Okay, this is the parenthesis that I left off of this notebook here. And now we can prepare to reduce the data sets. This geometry when we speak about geometry, we speak about the camera for gamma ray telescopes. But for water tank telescopes, the camera is the telescope. The camera are the tanks. So each tank is a pixel of our camera. Okay. We can also define the energy axis. Remember, the energy axis for plotting we define larger than the data we collect. And okay, this is another thing, another yet that will not be used in the future. So this will be included in the software. This will be automatic. Okay. However, now you have to set by hand the start time, stop time, the duration of the observation, a lot of stuff. But we have to do that here, but we will not have to do that in the future videos, okay? And finally, let's start the data reduction. I will not run it here. You can please run in your computers, but it can take some minutes to finish. And you can run until the end, and you see some results like this. These are the counts map, the excess counts, the exposure, and the background. Okay, maybe the striking plot here is the counts map that we see played, because we just built this empty object like we did yesterday for CTA. Okay, so it's empty because we didn't add the counts yet. We will see that in the second notebook that we will start working in a minute. Please let me know when you finish this, when you finish running. And if you have questions, we can discuss now. Yes? Yes. Yes, we have 4 sky regions, and each one of the counts map is for one different sky region. ICTP. Yes, everybody. Just another advantage of the water tank telescope that Leandro just called my attention is the direct cycle. For the imaging atmospheric Cherenkov telescopes, we have to observe only during periods of very dark skies without the full moon, unless you are working on specific projects. However, for the water tank telescopes, we have basically a 100% of the cycle. So we can observe during the night with full moon and also during the day with the sun. So this is another advantage of these telescopes. Despite the very large field of view, which is for the AACTs, you have 3.5 to 4.5 degrees. So how are we? Did you manage to it over? Okay, okay. So you can come to this this tab here and open the second Jupyter notebook. It's 2 ICTP simulate simple D1 log bar. Okay, you may see something like this. Okay, did you open the second notebook? Okay, so here we are simulating the detection of a source which have a spectrum of a log parabola. Okay, so we can well, we have to start by importing some libraries. You can shift enter and use all of these cells. We are choosing the array D1 because this is the array that we saved the data in the previous notebook. Here we are restricting the analysis from 1 to 100 dB, and this may be very useful when we are dealing with real data because the sensitivity of SWGO it basically starts at 1 dB. Okay, so we restrict our analysis from 1 dB to 100 dB, and we have to merge the 4 different slices of the sky that we analyzed first. This is something that, again, will not be needed in the future versions of the software. And here is the part that we can play, actually. Here we are defining a source that we want to detect. In this case, I'm using a log parabola spectral model. For those of you trying to simulate sources for SWGO, you can, for instance, look for the log parabola parameters of Fermi-LAT sources and try to extrapolate it to the SWGO gamma ray domain. Okay, this is an interesting way of trying to see if your favorite target will be detected or not by SWGO. Okay. Here I'm defining an array of fluxes. Actually, fluxes is not a good name. It's fluxes normalization. Just because I'm going to do a loop, so I take this spectrum and I simulate this spectrum from the weakest version of this spectrum to a powerful version of this spectrum. And okay, you can shift enter in these cells. This is a function, we don't have to go into details here because basically the complicated thing here is to plot, so you can take a deeper look on it later. But this is just to help us to plot the significance map. And then finally, we use simulate the source that we defined two functions below. Okay, so here with this fake function, we are creating these fake counts based on the log parabola spectrum that we defined in the previous function. You can shift enter, and shift enter, and you see something like this. Okay. So this is what we expect to see for this log parabola target that we defined a few functions ago with SWGO in 1 year. Okay, this is 1 year of observations. And if you keep pressing shift enter, you arrive to this loop here where I run over the normalization of the fluxes. So I get higher and higher normalizations and higher fluxes. So this takes some time, so I'm not running it here, but you can run it in your computers. And we have something like this. So this is how we can estimate the significance for different targets with log parabola spectrum. Okay. So here, of course, are the strongest targets, so they can achieve a significance of up to 12 sigma in the period of 1 year with SWGO. However, it's not. We don't have that many counts above 1 dB, so they are always very hard to detect. And that's the notebook. That's the lesson I have for today. Here are some exercises. You can try this, or you can play the way you want, and I can pass on your computer and we can discuss. Okay. So if you have doubts, just let me know, and otherwise, good luck with the exercise. Okay. because Okay, everyone. I see that several of you are playing with the tools very well, and you are changing the model to log parabola and increasing the index or decreasing the index, and you are doing very well. And that was the lesson for today. If you have questions about today's tutorial or the previous tutorial, feel free to ask me, okay? Or also to write me, okay? Well, if you are done, the lesson is over. At your time, okay? We have the auditorium is booked until 5:30, so in your time.